Hello dear students. So in today's session, I am going to talk about a topic which is usually not covered in your regular classes, irrespective of the institute in which you are studying. Of course, if you were at Vedantu, then this topic would probably be covered in your batch. If it wasn't, no worries guys, I'm covering it now. So the topic is about insertion of a dielectric slab between the capacitor plates. All right. So you may think that we are going to calculate the equivalent capacitance in such cases, but this session is beyond that. That is, we'll do it in the first 5-10 minutes and then we'll talk about a lot of other stuff. So let's get started right away. So first I will explain the situation to you. So guys, here in this figure you see there are two capacitor plates. They are present in blue color. All right, and then there is a dielectric slab that we are trying to insert between the plates of the capacitor. Okay, the plate dimensions are given. A and B are the length and width of the plate. Okay, the separation between the plate is D, and this dielectric slab exactly has the same dimensions so as to fit perfectly between the two plates. Okay, so this is the scenario. The figure depicts that we are done inserting the slab by a distance x. So we have already inserted the dielectric slab by a distance x between the capacitor plates, and in this position, what is the capacitance right now? Let's first try to calculate that. All right, now in order to do that, tell me guys, can we say that this part this part is one capacitor, this part is one capacitor with a dielectric slab in between, and the lower part is another capacitor with air in between. So I'm talking about two capacitors, C1 and C2. The C1 capacitor has plate area of X multiplied by A. All right, and the C2 capacitor has a plate area of A multiplied by B minus X. Okay, this height would be B minus X. Okay, and these two capacitors would be said to be connected parallelly, and using this we can calculate the equivalent capacitance of the system right now. So we'll start by doing this. So C equivalent will be C1 plus C2, and now C1 can be written as the plate area, which will be X times of A, this is plate area, into the dielectric constant, which would be epsilon naught into K, divided by the separation between the plates. And similarly we can write C2. To write C2, the plate area will be taken as A multiplied by B minus X, and then the dielectric constant will be epsilon naught, as there is air between these plates. Okay, the separation between the plate is G. Okay, so this is the capacitance that we are getting, and now I plan to collect the terms involving X together. In fact, I see A epsilon naught by D as the common quantity in both these terms. So whatever I am taking out as common quantity, let me strike it out from here so that I don't commit a mistake. Okay, now what is left here is Kx minus X. So we will write, okay guys, okay, so we will write K minus 1 into X, K minus 1 into X, and here we will have a plus B. Okay, so this is the capacitance that we are getting. This is the equivalent capacitance in this position. Now let's understand this, that the equivalent capacitance, let me write it as C. This is the function of X. Not only that, it is a linear function of X. Okay, it is a linear function of X, and because K is always greater than 1, okay, greater than or equal to 1, this number will be a positive number. So C increases with X. As this dielectric slab is being pushed between the capacitor plates, the capacitance of the assembly is increasing, and the increase is linear. Okay, when X is 0, you can say that the capacitance that we have is A epsilon naught B by D, which is the default thing that we write. Let it be C naught. Okay, and when X attains maximum value, the maximum value will be equal to B. So when X becomes equal to B, we get the capacitance as A epsilon naught K into B by D. Okay, which basically becomes K times of initial value. So what we can say is this, that as X is increasing from 0 to B, the capacitance is increasing from C naught to K times the initial value. In other words, if I were to draw a graph between capacitance and X, okay, then this graph would look somewhat like this. It would be a linear curve which will start from a value of C naught, which will go till a value of K C naught, as x goes to the value of b. So this would be the graph. So keep this in mind because we are going to use it. Now guys, there is one very important aspect to keep in mind right now. Let me come back to the figure. Capacitance of a capacitor is property of the geometry and the material, the dielectric that we have put between the capacitor plates. It is not dependent on the fact that whether we have connected the battery or not, whether the capacitor was previously charged or not. So these factors do not affect the capacitance of the assembly. All right. And therefore we were able to calculate capacitance even without talking about whether the battery was connected or not, okay, whether the charge was present on the plates or not, because the capacitance doesn't depend on those factors. But once we have find out the capacitance, once we have found how capacitance changes as the dielectric slab is being pushed or it is allowed to get between the plates, we know that the capacitance increases linearly. We are going to make use of it. Now guys, we are going to discuss two situations. Okay, we are going to discuss two situations. Let me told and we are going to discuss these two situations as examples. Please understand this. I am not saying that these are the only two situations that you will come across. You may come across different situations than this also. What I am telling you is that I am going to deal with two most common situations, and the way in which I am dealing with those situations, with these situations, will give you an idea of what you should be doing if an altogether new situation comes to you. So that is the first thing. So I'm going to discuss two situations here so that I can demonstrate what you need to do when you are faced with a new situation, with an altogether unknown situation. Secondly, because these two situations are most common ones, so whatever results we get, we can actually learn them as standard results, because there are good chances that if a question comes on this topic, the two situations that I am discussing, probably it will come on those situations only, probably, not surely. Okay, so what are those two situations? Okay, so two situations that we would be discussing, okay, are, okay, first, insertion with battery connected. Okay, like we are inserting the dielectric slab, so while the battery is still connected, so in the insertion with battery connected, insertion with battery connected. Okay, and second would be insertion after removing the battery. Like we connected the battery, we allowed the capacitor to get charged, and then we removed the battery, and now we are inserting the dielectric slab. So insertion after removing the battery. Okay, so these are the two situations that we will discuss. Okay, let's get to the first situation. So insertion of dielectric slab with battery connected. So guys, you see three figures here. Okay, this A figure demonstrates the starting process. Like we have just begun inserting the dielectric slab within the plates. Okay, so in this situation, X is 0. Okay, in this situation, then the third figure, the C figure, demonstrates the event when the slab is completely between the plates. Okay, so this is the case when X becomes equals to B, and this is a general scenario when X is more than 0 but it is not yet equal to B. Okay, so what is happening, like as the dielectric slab is being inserted, what exactly is happening? Okay, so I'm going to discuss situation A and situation C first, and then later on we are going to talk about situation B because it is a more general situation. Okay, now guys, to begin with, if I ask you to distribute potentials in this circuit, like if I ask you to write potentials of various points in the circuit, how will you start? Okay, for example, if I ask you to write potential, like if we consider zero potential here, okay, if we consider zero potential here, then if the EMF has a if the EMF is E, okay, then we will have E potential here. Okay, now in C figure, if I ask you to distribute the potential, you will still do the same thing. Like if this is zero potential here, okay, there would be E potential here, you will still do the same thing. Okay, the same thing is valid for situation B also. We can write it here, but we will talk about situation B later on. Okay, so guys, whether it was situation A or B or C, the battery mandated that the potential of one of the plates should be 0 and the potential of the other plate should be E. Or rather, I should say that the battery mandated that the potential difference between the capacitor plate should be E, whether it was this situation or this situation or this situation. So what we can say is that in this case, the governing equation, the equation that will decide all other parameters, that equation is that the potential difference should remain equal to E. Okay. So if I try to make a table in which I will be filling different parameters corresponding to stage A, B and C. Okay, let's do that. So in stage A, X is 0. In stage C, X is B. In stage A, capacitance is C naught. In stage C, it is K C naught. I hope you understand. Okay, then potential difference. V is the potential difference across the plate. This is E and this is still E. And this is actually the governing condition. That means every other parameter will change its value so that this condition can hold good. That means the potential difference can remain equal to E. Every other parameter has to change its value accordingly. For example, the charge on the capacitor plate, initially it was C naught E and now it would have become K times of C naught E. So to maintain the potential difference same, the charge increased. All right. And how much additional charge came? That was K minus 1 into C naught E. So this is the additional charge, the difference of these two. This is the additional charge that has come to the capacitor plates. What was the potential energy of the capacitor? The energy stored in the capacitor, that was half C naught E square, and later on it become half K C naught E square. So the energy stored in the capacitor has also increased. Of course, there was an increase in charge. We can expect that the energy would have increased. So the increase in energy is how much? The increase in energy is half C naught E square and then K minus 1. So energy has increased by this much amount. What about the electric field between the plates of the capacitor? So electric field was potential difference divided by the distance between the plate. It is still the same. It is still the same. Okay. Now guys, there may be situations or there may be values that I have wrote here that might be confusing you right now. Like you might find them odd right now. It may happen. Some of you may have agreed with the entire table. Some of you may have they are still wondering that how it can happen, but I will explain everything. Okay. So this is what has happened. To ensure that the potential difference remains same, okay, the charge has changed accordingly, the potential energy has changed now. Okay, but there are things to be discussed right now, like exactly what is happening. I don't get it exactly what is happening. For example, there are many questions to be answered here. Okay, for example, this is the increase in potential energy. Okay, okay, I'll come back to what we need to answer. So before we move to stage B, okay, before we or should we move to stage B? Should we move to stage B? Yeah, let's write for stage B also, and then I'll try to understand. Then we'll try to understand. So here X is some intermediate value. Okay, here X is some intermediate value. Capacitance is something that we wrote earlier, Ka epsilon naught by D, and then K minus 1 into X plus B. Okay, the potential difference will still be E. The charge would be the product of these two. So it would be A epsilon naught E by D and then K minus 1 into X plus B. Okay, the energy would be half CV square. So half A epsilon naught by D and then K minus 1 into X plus B and then E square. Okay, electric field will still be. So we have written the values, but I want to understand better what is happening. I want to understand better. So guys, now let me throw some clarity. Let me throw some light on what is happening. Okay, please pay attention. So this is a capacitor plate with no dielectric inside. Okay, so this is the capacitor plate. We connected a battery, okay, of EMF E. The consequence was that there was charge here. Okay, there was some charge here. Same value of negative charge came here. Okay. And there were electric field lines here. I'm ignoring fringing. So there would be electric field lines here. like this. Okay. Now, okay. Now there was a dielectric slab here which was outside right now. As of now, it was outside. Okay. The dimension, like there is less space for drawing, so the dimension is same as the dimension of the plate. Now we started pushing it inside. Okay, let's try to see what happens. Okay, so when this slab, when we push it inside, or when we allow to go it inside, let's say it comes to this region. Okay, this is X. Let's try to understand. There would be polarization in this dielectric. Okay, like there would be induced polarized charges here. Say negative charge will come here, positive charge will come here. Okay, and because of that, the electric field will tend to decrease. Okay, because of these opposite charges, the electric field in this region will try to decrease. Okay, but if the electric field in this region decreases, then the potential difference as we move from this point to I had the eraser chosen. I'll Yeah. So if the electric field decreases, if the electric field in this region decreases, then as we move from plate 1 to plate 2 through this region, there will be lesser potential difference as compared to what we will witness here. And this cannot happen. It cannot happen that the same plate can have two different potential. Like when I move from this to this, I have a different value of potential difference. When I move from this to this, I have a different. This can't happen because the plates are same. So whatever potential difference we get here, the same potential difference should be getting here. So how will that happen now? Okay, how will that happen? Like whatever I've done till now, I hope you understand that. Okay, I'll repeat it. I started pushing the dielectric down. As soon as the dielectric enters the capacitor plate, it enters a region where electric field was already present. That electric field will cause polarization. Because of polarization, the polarized charges will appear. That will try to decrease the field here. The field will decrease, but the field can't decrease. So what will happen is that the moment field begins to decrease here because of polarization, battery starts sending additional charge, and this additional charge comes and resides on the region where the dielectric has come. Why? Because this charge has to neutralize the polarized charges. Like this new charge has to polarize the it has to neutralize the effect of polarized charges, so that the electric field value can be maintained at the previous value. Are you able to understand this? So as you are pushing this dielectric more and more inside, okay, the regions where the positive where the charges should be, okay, the regions where the charges should be, that region is also increasing, and ultimately when the entire dielectric slab comes inside, the charge density again becomes uniform throughout the plate. Okay, please understand this. Okay, I'll reiterate, guys. When the slab is partially inserted, watch carefully what is happening as far as the charge distribution is concerned. Okay, when the slab is partially inserted, there is high charge density on this region, low in this region. Why it is high here? Because there is some negative charge present here, and the net value of these two has to match the net value of this. Are you getting it? The net value of these two has to match the net value of this. Therefore, we have more positive charge here because it has to take care of some negative charges, such that the net sigma here and the net sigma here can become equal, and we may get the same field. So I hope this explains everything. That as I said, that as we are in the process of insertion, the region up to which we have inserted, in this region you will find that the charge density is more as compared to the remainder of the region. Okay, why? Because to keep the electric field same in this region, we will need more charge, because there is a dielectric present here. The presence of dielectric tends to reduce the net field. So to compensate that, the charge will be more. When the slab is completely inserted, like when it was completely outside, there was some density. Okay, as you started inserting it, the density began to increase. When you have completely inserted it, the density on the entire plate will increase, and it will again become uniform. It will again become uniform. So all these values will happen. Okay, now there are few points that requires explanation. One point is that if we calculate the work done by the battery, if we calculate work done by the battery, this would be delta Q, like work done during the insertion process. This would be delta Q into E. So it would become C E naught and then K minus 1 into E naught. So it would become C E naught square into K minus 1. Okay, this is work done by the battery. But delta U increase that we wrote here. See, delta U was half of this value. It was half of this value. It was half C E naught square K minus 1. Now, obviously, the question that we should ask is, if battery supplied this much amount of energy and capacitor stored only this much amount of energy, where did the rest of the energy go? Okay. Now, the usual answer in these cases is that students reply heat. Heat is generated. But guys, no, I'll tell you exactly when heat is generated. Like, how will you decide whether there is a possibility of generation of heat or not? Okay, I'll tell you the answer to this also. In this case, heat is not generated. Okay, most of you believe that when the teachers don't find a reason to account for energy conservation, they say that the dissipated amount went in the form of heat. And when the energy conservation is taken care of, there is no heat generated. Okay, so they use heat as an escape plan. Okay, an escape plan of explanation, but that is not the case, guys. There are a few things based on which you can decide whether heat will be generated or not. In this case, I'll have to explain that. So I'll do that in a short while. Before that, I would like to explain one thing. See, if the potential energy in a general situation, like if we talk about the potential energy in a general situation, it does look like a function of x. Okay, the potential energy does look like a function of x. Or in other words, I would expect that the plates of the capacitor might exert force on the dielectric slab. Okay, it seems like that because dielectric slab will have polarized charges. Okay, so it is quite possible that these negative charges experience attraction, these positive charges experience attraction, and therefore there might be a net force of attraction. So can we try to write that force? The answer to that question is yes. We will write that force. I will do that. If you don't understand the explanation, at least remember the result, because the result is what you will be using. Okay, so my intention is to write the force. Okay, now the assumption is that let's forget the gravity. First of all, let's forget the gravity. If this slab is being pulled inside by the capacitor, okay, I want to write this force. What I will do, I will use this. That force can be written as mod of du by dx. Guys, this is not the best of explanation that I'm giving you right now, but it is in your interest to not go into the best of, because we will digress from what I want to tell you. I just want to get to the expression of the force. This is a good enough explanation, not the best of explanation, but good enough for now. Okay, so it will become a epsilon naught by 2d, okay, and then e square. Okay, and then it will become k minus 1. You check this, everyone. The most important part is that it is coming to be a constant. Now keep in mind, guys, I'm not saying that the force always comes to be a constant. For example, I told you that we will be discussing two situations. This is the first situation that we are discussing. In this situation, the force has come out to be a constant. It doesn't mean that the force will always come out to be a constant. Now I want you guys to remember this value. Okay, I want you guys to remember this expression. Okay, and now let me explain everything. Like, I will do a question, and in doing the question we will actually understand a lot of things. Let me remind what is yet to be understood. Heat, we did not talk about why they are unequal. Okay, where does the rest of the energy go? We are yet to talk about that. So let's try to understand that. And for that, based on the situation that I was going, a question is written here. It is written, the slab was released from stage A at t equal to 0. Mass of the slab is m. There is no gravity and friction is absent everywhere. Find the time taken to achieve stage B. It should be actually stage C. Okay. So guys, I'll tell you exactly what the question is. So um, this is the capacitor plate. Battery is here. Okay, the capacitance is C naught right now. This is E, and uh, this is the capacitor. This is the dielectric slab. Okay, this is stage A. Okay, we release the slab in this position. There's no gravity. There's no gravity. Okay, but because the capacitor plate can attract the dielectric will start getting inside the capacitor, and there will come a time when the dielectric slab would be like this. Okay, and remember the plate dimensions that we are considering. The plate dimensions are, this is A and this is B. Okay, so this is situation B. Now going back to the question says that slab was released from stage A at t equal to 0. Mass is m, there is no gravity, friction is absent. Find time taken to achieve B. Now my question to you is, guys, we found out that the force is constant. Okay, so constant force will result in a constant acceleration, and under the constant acceleration, this is slab covered a distance of B. Okay, so the constant acceleration would be like the acceleration. Okay, it would be force upon mass. So it would be A epsilon naught C square into K minus 1 upon 2D. Let me just check whether I wrote the expression correctly or not. A epsilon, I think it is correct. Okay. Okay, so I divided with M. Okay, and now I will use displacement is equals to half into acceleration into t square. So the time would be 2b by a. Okay, so it will become a epsilon naught e square into k minus 1 into 2dm, root of this. Okay, so this is the time taken by the slab to come to this position. Now the second question is, by this time, can we say that the slab would have acquired some speed, let's say v1? Okay, obviously it would have, and this speed can be written as, again, you can write it in, because the acceleration is constant, you can use root 2as. You have already found the time, you can use acceleration into time. Okay, so there are multiple ways. So if we use acceleration into time, okay, what will happen? The time was, it will ultimately become root 2 into displacement into acceleration, which is a epsilon naught e square into k minus 1. Okay, divided by 2 dm. So this 2 gets cancelled. Okay, so this speed is coming out to be root of a b epsilon naught e square, okay, k minus 1 upon dm. Okay, now this dm is not d of m, it is d into m, like distance into, it is not infinitesimal mass, it is d into m. So this is the speed. Okay, next, if we want to calculate the kinetic energy, we have the speed, we have the mass. So the kinetic energy would be half m v1 square. So it would become half m into, okay, v1 square. So from here we will pick a b epsilon naught e square into k minus 1 upon m into d. M gets cancelled. Okay, so we end up getting a b epsilon naught e square k minus 1 upon 2d. Wait a minute, guys. AB epsilon naught d, that's c naught. Okay, so c naught e square k minus 1 by 2. Okay, is this the missing energy? Okay, battery did more work. The amount of energy stored in the capacitor was not equal to the amount of work done by the battery. It was half of that. Okay, so is this the missing piece of the puzzle? So yes, so the difference went into the kinetic energy of this slab. Okay, now if there are questions popping up in your mind, why did we not talk about the kinetic energy in any of the previous case when heat was generated? So let me tell you this. So guys, you do check the time here. Okay, the time is finite. We are getting some finite value. All of these are finite numbers, so we are getting a finite value. So as the slab entered the capacitor plate, it took some finite amount of time, and it was this finite amount of time in which the charge flew through the circuit. right? Heat generation happens only when either there is a resistance in the circuit which is not there here, or there is a flow of finite amount of charge in infinitesimal amount of time. So you can look back at all the explanations that were given to you, or all the situations where it was mentioned to you that heat will be generated. Okay, in those places either there is a resistance present in the circuit, or there is some flow of charge happening in negligible amount of time. Getting it? Okay, for example, you must have done questions like there are two spheres, one is charged, the other is not. We connect them with a wire, and then as soon as we connect them with a wire, the charge gets shared between the two. Some charge flows from first to second, and in this case heat gets generated. In this case, when we try to calculate the original energy, the initial energy of the sphere, and then we check out the final energy of both the spheres, we discover that the energy has decreased. The initial value was more as compared to the final value of both. Okay, so there was definitely some loss in energy. So we say that the loss happened because of heat. Here, why did not we say that? Why did we look for areas where the energy could have gone? Because we under the conditions we can see that it will take some finite time. If we release it will take some finite time. Okay, now let us see that if I want to convert it into a case where the heat will be generated, what is needed to be done? Suppose I say that this slab is massless. Okay, why I want to say that? Because taking it massless will render it incapable of bearing kinetic energy. Something which is massless cannot have kinetic energy in it. So I'm making arrangements to ensure that my slab cannot have kinetic energy, because I'm disliking this idea. I want the heat to be generated. So I'm disliking the idea that the capacitor, the dielectric slab is getting the energy. So I made it massless. If you say that, okay, we are using a massless slab and we are releasing it, the time in which the slab will get inserted becomes 0, because m is 0 now. M is 0. So the time becomes 0. So now we are again saying that a finite flow of charge is taking place in 0 time. Now heat will be generated. So what will happen is that the moment you release it, it's a massless entity. Even if it experiences any amount of force, it will just blast. It will just go shatak into the. So it just comes here and stops here. Okay, why did it stop here? Because it has no inertia. Okay, so it comes here, it comes down and stops. Like the moment it will try to get out, there will be some force on it which will try to stop it from getting out, and because it is massless, it can have infinite accelerations, so it will just stop here. So it went into the capacitor plate in a flash, and therefore now heat will be generated. Okay, all right. Sir, what if I hold the slab and then I allow it to go down slowly? What happens in that case? So if you hold the slab, then in holding the slab, you are exerting an upward force and you are allowing the slab to go down slowly. So you are doing negative work now, because your force is upward, displacement is downward, which means that you are gaining energy from the system. Doing positive work means supplying energy, doing negative work means gaining energy. So if you are holding the slab and then you are allowing it to go down slowly and slowly, you are applying an upward force, displacement is downward, so you are doing negative work. That means you are absorbing the energy from the system. So by the time you would have allowed this slab to come into the position B, you would have done an amount of work which is equal to this value. That means whatever energy would have gone into the kinetic energy of the slab, you have absorbed that energy now. Okay, now continue. I hope you are understanding everything now. Okay, and the heat explanation is clear, I hope. Now what if we don't do anything? We'll let this situation continue. So by this time the slab has got inserted. Okay, it has acquired some kinetic energy, it has mass, so it can do that. It has some inertia, so it will overshoot this position. And the moment it overshoots, now the direction of force will change, because the capacitor plate will always attract the dielectric slab. Okay, so it will overshoot now, and the acceleration will reverse. So it will come down, slowing down, and it will stop. It will exactly come out like whatever amount we inserted initially, exactly that much amount will remain inserted, and the slab will come to momentary rest. It will then again be pulled up. Okay, then again the same thing will repeat. So what I'm suggesting is that we will witness something like this. Let me make diagram. So I'm deliberately making small diagram. Okay. Oh. Okay, so this was our starting position A. This is our next position B, in which it is moving with V1, which is actually maximum. Here the slab is almost out, speed is 0. Okay, this is position C, and then it goes into this position. Okay, now the speed is upward V1, and then it again comes to this position. Here speed is 0, here speed is 0, which means here kinetic energy is 0 and potential energy is half C naught E square. Okay, here potential energy is half K C naught E square, and the kinetic energy is half uh, uh, C E naught C naught E square into K minus 1. Yeah. Okay. Yes. Okay. Here again the kinetic energy is 0. The potential energy is again half C naught E square. Okay, and then here again the same values, So guys, what is happening here? As we go from this position to this position, battery supplies energy to both the capacitor and the dielectric. When we come from this to this, here the battery was supplying energy. Now both of them are giving the energy back to the battery. The capacitor is giving its electric energy back to the battery. The slab is giving back its kinetic energy back to the battery. And here again battery is supplying energy to both, and here again both of them are returning the battery. So here battery supplies energy. Okay, here battery supplies, then here battery takes back. Okay, battery takes back. Okay, here again battery supplies, and here battery takes back. Okay, the time needed to move from this to this, we calculated the same time. So if we are asked about the period of oscillation, then that would be 4 times the time that we calculated. 4 times of this value, that would be the period of oscillation. Are these oscillations simple harmonic? No, they are not simple harmonic. Okay, because in simple harmonic motion, acceleration depends on the displacement. Here the acceleration was constant, except the change in direction, the magnitude of acceleration has always been a constant. All right, so I hope that clarifies everything regarding the situation A. Now let me quickly take up situation B. In situation B, we were saying that the battery has been removed. So what will happen here? Okay, so we first charged the capacitor. We have charged the capacitor, and now because we have removed the battery, so there is no place, there is no route for the charge to flow. So in this case, the governing condition would be that the charge on the capacitor plate remains constant. So again, 3 stages. Okay, and again we will decide different values. So in stage A, X is again 0. In stage C, it is again B. Okay, here the capacitance is again C naught. It is K times of C naught. Here, before we can talk about potential difference, we need to talk about the charge. Whatever charge was present on the plate, that remains same, and this is the governing condition. That means other values need to change keeping this in mind. For example, the potential difference between the plate, now it was earlier Q naught by C, it has now become Q naught by K C naught. So the potential difference has decreased, which is logical also. Why? Because the same charge is here. Q naught charge was present here. Q naught charge is present here. Q naught charge was producing some electric field in vacuum, and now the same charge is producing some electric field in a medium. So obviously the field will decrease. The net field will decrease by a factor of K. Why it didn't happen in the previous case? Because the charge increased to compensate for the reduction in electric field, to maintain the same value of electric field. in the previous case. Okay, now energy, previously I was using half CV square because V was constant. This time, because charge is constant, the preferable formula to use would be Q square by 2C. So you can see that the energy has decreased. Okay, energy has decreased. Okay, now where did the energy go? Okay, so in this case also, like qualitatively we can argue, once you release the dielectric, it is being pulled inside. If there is no external agent, if there is no friction, there is no gravity, so this pulling act is done by the capacitor. So capacitor has got a fixed amount of energy. There is no battery to supply any more energy. So whatever kinetic energy this slab will gain, it has to come from the capacitor only. All right, and how much that kinetic energy would be? So the difference of these two would be the kinetic energy acquired by the slab. Okay, electric field, so it would be Q naught by C naught D. Here it would be Q naught by K C naught D. Okay, so electric field has decreased as expected. Okay, so that is what is happening. If we talk about situation B, okay, the X has got a general value between 0 and B. Capacitance is again A epsilon naught by D, and then K minus 1 into X plus B. That is capacitance. Potential difference, we wrote potential difference as Q naught by C. Okay, C will be this, so potential difference will become function. Charge will remain Q naught. So this is Q naught square by 2C. C is A epsilon naught. D will go in the numerator. K minus 1 into X plus B. Okay, I specifically wrote U to highlight the fact that if we now try to calculate force, okay, I leave the math up to you. You will find that this is not a constant. Okay, this is not a constant, and therefore from an examiner's perspective, I'm telling you, you will not generally find kinematical questions on this situation. What do I mean by that? In the previous case, I asked you about the time taken by the slab to enter, the velocity acquired. Velocity can still be asked, but any calculation involving time requires integration when acceleration is not constant, and that will consume, like, that would be a very mathematical question to ask, you know, to check your physics. So generally from an examiner's point of view, I will not frame kinematical questions, like questions which are asking about time. All right, how much time the slab took to go from this point to this point. I will not ask that because the force is not constant. Okay, I may still talk about speed. Why? Because to calculate speed, I can bypass the integration by paying attention to the energy. Remember that the calculation of time is a complex thing. Like when the forces are not constant, calculation of time requires more effort as compared to the calculation of speed, which can be done on the basis of energy. All right. So guys, that's it from my side. I guess I tried to explain both the situations to you. You will find many questions on this particular topic. There are some present in HC Verma also. If there is a question on force, usually the situation that is given is the first case when the capacitor is connected to the battery and then we are trying to insert a dielectric slab. Okay, so that is the usual situation that is given. I hope I was able to explain that properly to you. And if a third situation comes, then what is the general rule? Please identify the governing condition first and keep that in mind, and all the other parameters will change accordingly. So that is the general rule that you have to keep in mind. With that, I will end today's session, guys. You will find me with more such sessions that will help you ace the JEE advanced examination. Take care, students. Bye-bye.